Yeah, so hi everyone, I'm Carl at the University of Illinois. My advisor is Professor Hu, sitting up here at the front. And today I'm going to talk to you about two separate topics, really. One topic is that we've worked with some science teams in the past, over the past few years, helping them accelerate their codes on GPUs on Blue Waters. And so what we're looking at as a research group now is we're starting to look at some more advanced systems with multiple CPUs and multiple GPUs. And so we wanted to take some of the existing codes and run them on some of these newer GPUs just to get a sense of how they'll perform. So that's going to be kind of the first half of this. And the second half is looking at some of these maybe next generation supercomputers that are coming online this year, and some of the communication performance complexities that are going to come along with those systems as they add more CPUs and GPUs. And that's, there's been some talk about maybe a second Blue Waters machine, and so we don't know what that machine would look like, but we can kind of take a guess based on some of the changes that are coming with some systems like Summit and Sierra. So just to kind of give everyone a quick refresher, maybe I'm preaching to the choir here, but I know a lot of people use Blue Waters, also don't use GPUs. So this is kind of how I get to look at a Blue Waters node. So on the right-hand side is the GPU. And so basically, GPU has a bunch of these SMs, which you can kind of think of as similar to CPU cores. And there's going to be like 10 to 100 of those. And within those, we have a register file, some shared memory, and a bunch of SIMD execution units. And the GPU has its own memory subsystem. And it's connected through some kind of interconnect, and this is kind of what I'm looking at the performance of this in the second half, to the rest of the Blue Waters node. So the network and the hard drives and the CPU is all over there. So it's just kind of keep in mind while we're looking at this. And so on Blue Waters, we have GPUs that use NVIDIA's Kepler architecture. And so that's on the right, and those GPUs have 15 SMs. And so the current cutting edge of NVIDIA's GPUs, which are going to be in Summit and Sierra, which maybe are coming online this year, are Volta GPUs. And so this is kind of, without getting too dirty in the details, the Volta GPUs are going to have many more SMs. And so this is 84 on the left and 15 on the right, so that part's accurate. The Volta SMs are a little smaller in some ways, so we can see that the Volta SMs actually have fewer CUDA cores in them, but there's many more of them on a GPU. And another important difference on these next generation GPUs is the amount of memory bandwidth that's available to the chip. And so on Blue Waters, we have about 250 gigabytes per second of GPU memory bandwidth, and on newer GPUs, we're going to have 900 or maybe even more. This is a change in memory technology that's enabled this. And so because of the amount of SMs on the new GPUs, the total, the theoretical floating point performance rate is much higher on these GPUs. So each SM maybe can't do a lot more, but there's a lot more SMs available. So if you can make use of them, then you can get a lot more throughput. And that's, this is sort of one of the challenges when we're switching GPU generations. When we worked with some of the science teams, what we discovered is that people had spent a fair amount of effort. Maybe this is the first pass of CUDA code that they wrote. Kepler was the first real serious compute architecture that NVIDIA had out, and so people spent a lot of effort tuning their code to particular architectural parameters on Kepler. And so when we move from Kepler to Volta, what we see is that these architectural parameters have not sort of grown in a uniform way. So if your code took advantage of the fact that there were a certain amount of SMs and maybe each SM had 1/15 of the aggregate memory bandwidth, when we move over to Volta, we can see that the total memory bandwidth goes up by a factor of 4, but the number of SMs goes up by a factor of 6 or something like this. And so the growth in performance that we get maybe is not what we would expect just by reading off the spec sheet. So this is a challenge that we saw. In some sense, people have over-optimized their code for Kepler. We try to move them to new GPUs, and we run into performance optimization challenges. And so specifically, I'm going to show results from two of our previous collaborations. So one of them was with Tom Jordan and Yifeng at the Southern California Earthquake Center and USC, and that's an inelastic wave propagation code. And another one is ChaNGa at the University of Washington with Tom Quinn, and that's an n-body gravity solver. And so I'm not going to get too much into the details of the optimization that we wanted to make, but just to give you a sense of the kind of results that we see. And if you run GPU code on Blue Waters and you move it over to another system, you might see something kind of similar. So this is the V100 is the Volta-based accelerator that will be in some of these new systems. And so the Speedup over K20X, which is what's in Blue Waters, is somewhere around 5 for both of these codes. And that's really just the, that's not just the kernel speedup, that's the speedup of maybe an iteration of their iterative solver or something. And so just to give you another sense, I'm not really going to talk about this, but there's the preceding accelerator to the V100 is the P100. And so you can see that we also were able to test these moving just on the P100. And so the speedup is not necessarily sort of well-behaved, right? AWP got less speedup over the P100. There was a lot of speedup going from K20 to P100 and not so much from P to V. And so it just depends. This is related to these changes in architectural parameters. And so this is with very minor changes from the Kepler code to the Volta code. So we investigated a few different things to try to improve some of these performance numbers, but the problem that we ran into again is that so much effort has been put into optimizing some of these codes for specific architectures that we kind of have to tear out a lot of the algorithmic choices and maybe re-implement them to change the speed up. So this is really just, we took the code that had been optimized for Kepler, ran it on Volta, and this is the performance that we got. And I can go into a little more detail in one of these. And so on K20, so there's 2 big kernels in this code that took up most of the time, and that's this GPU timeline here. So you can see that almost adds up to 100%. And on the Kepler system, this is a case that we call it so-called latency limited code. And this is pretty typical in our experience of working on these codes, is that when they're highly optimized, we run into cases where the GPU is frequently stalled waiting for specific, waiting for data that it needs or something like this. And on K20X, we often run into cases where people do a lot of work, and fundamentally, we might expect these codes to be memory bandwidth limited, but we can only maybe get 60% or so of the global memory bandwidth in practice on these codes. But one nice thing is that when we move over to Volta, we see that the memory system on Volta tends to be much better behaved. It's much better at getting performance when the memory accesses are not so great. And so if you're finding that you're having trouble with that in your GPU codes, then moving to Volta can be quite beneficial for you, even without making any other changes. So what we observed is that when we moved over to Volta, we became memory bandwidth limited without really making any further changes. And so one thing, this is sort of a pretty common pattern, is that when this Kepler optimized code, the GPUs were not as enormous as they are now. And so our parallelism typically can be at kind of a big granularity of thread blocks. And this is nice because within that thread blocks in the CUDA programming model, it's easy to the bigger the thread block is, maybe the more potential we have to reuse data within that thread block. And that's the easiest kind of reuse to capture. But the problem is that we can't run that many thread blocks on a particular SM because the size of those thread blocks require a lot of hardware resources. And so that's not such a problem on Kepler when we don't have, when the GPU isn't as big. But when we move over to Volta, we find that there's a lot of SMs, and we can run. We want to be able to either make our problem bigger or we need to use more of these SMs, and so. Even if our SMs have some more resources, we're limited by particular factors in our previous code, and we can't really make full use of this bigger GPU. And so we run into this case where we have this trade-off where it might be nice for Volta to sort of reduce the granularity of our parallelism to make it more fine-grained. But the problem is the trade-off is then it becomes harder to capture some reuse in the code. So it's not entirely clear what the right direction to go for each of these is. So kind of what we've observed, though, over this is that you can kind of take two approaches when we're porting the GPU over. Code over. One, you can kind of just do nothing. And if you run it, you'll get something like a 3 to 5x speed up in both the kernel speed up. And also, I just wanted to note that I'll talk about this a little bit more in the next 10 minutes. But there's also roughly a 3 to 5x speed up in the interconnect between the CPU and the GPU. And so this kind of corresponds pretty nicely. And if you're lucky, you know, some people, when they run code on Blue Waters, they pick a particular problem size because that's the most they can fit in 6 gigabytes of memory. And so if we move that problem over to Volta, it's not big enough to fill that GPU. So if you're set up in a way where you can just run a bigger problem on the GPU, the Volta GPUs have more memory, and so maybe you just make your problem bigger, then you can fill up all the SMs. You know, if you're willing to spend your grad students' time on rewriting the CUDA code, probably the right approach is to make the parallelism a little bit more fine-grained, do more tasks that are smaller. It's a little harder to capture some data reuse, which is the key to making the performance good, but it also makes it easier to fill the GPU, and NVIDIA is not really showing any signs of you know, going back on this pattern of putting more and more and more, possibly smaller SMs on their GPUs. So this might help the code scale more in the future as well. So there's another dimension to this, which is the future nodes are not really going to look like a node that is on Blue Waters. So right now we have on a Blue Waters XK node, which is the GPU node, we have one multi-core x86 processor coupled to one GPU through a PCIe 2 interconnect. And so the unidirectional bandwidth on that interconnect is 8 gigabytes per second. But when we're looking at a node that's coming online on a supercomputer this year, we'll see that it has 2 Power 9 processors, so close to 3 times as many floating point units across the 2 CPUs, many more hardware threads. So if your code is bound by memory bandwidth or memory latency, then we have many more hardware threads that can be stalled. When one thread is stalled, we have another thread that can take its place, so maybe making use of all that floating point is useful. But we have 6 GPUs, each of which is vastly more capable than the GPU that's on Blue Waters. And furthermore, the interconnects between the CPUs and GPUs, A, the topology is more complicated, and B, the interconnects are much faster. And also, this is going to be popular with a lot of people, is that the systems are going to have like way more system memory. So this is a little cartoon of what they look like, but on the right we have Blue Waters, and on the left we have Summit. And so there's a particular topology. These processors are also connected by an SMP bus. That is, on this system, this bus is going to be 64 gigabytes per second approximately. And remember, each of these links is 50 in a particular direction. So it's pretty well balanced. But you can imagine that maybe communicating data from this GPU to this GPU could be much slower than communicating data from this GPU to this GPU. Even if the links have the right balanced aggregate bandwidth, there's more of these links. And so what we wanted to do was investigate sort of what happens on systems that look like this in practice. And so we have a few different research projects going on, and you can check these out. One of them is a set of CUDA micro benchmarks, and I'm going to emphasize the GPU intra-node communication. But we also have a few other things in here, and we're still working on expanding these. We also have a great variety of detailed information about neural networks, and I know there's several science teams looking at neural network performance, and so you might want to check this out. This has a bunch of different neural network performance on different machines, different frameworks, and different operations, so that might be of particular interest to you. And this is sort of as to serve as a foundation for figuring out what architecture should look like for particular workloads, and how people should run specific neural network architectures that they're interested in. So this is sort of foundational work for that. So first, faster interconnects. This is a system on the right which is actually twice as fast as Blue Waters. So I want to make that. And this system on the left is 1.5 times as fast as Summit. So this comparison is actually the comparison of Blue Waters to Summit is actually worse than this, or worse than this. But So you can see here we have, there's a variety of different ways you can transfer data around in GPU systems. And so each of these links is a different method for moving data from a CPU to a GPU. And so you can see that we can get a lot, in some cases we can get a lot of the theoretical bandwidth. Some of these curves, this blue one is actually sort of the most common way. You just do CUDA malloc, CUDA memcopy. Its performance is pretty odd. So it's not even really what it says on the tin that you get. But the important part is that the new next generation systems, the bandwidth is much higher. So the top of this graph is right here on this one. So, and there's also new capability that is technically present on Blue Waters, but the implementation has changed a lot for newer GPUs. There's something called unified memory, where you can make a particular kind of allocation. It can be directly accessed on the CPU and the GPU, so you can delete all the mem copies from your code. So you can imagine how that would make it easier. You could have some pointer chasing data structures and everything just works. So that's great. It's kind of nice. It works at the page granularity. So whenever a device accesses a particular page, that page gets moved over to the device. By the time these new systems come online, it might be even more sophisticated than that. It might detect which pages are hot on which devices and make some smarter decisions about where to go. So one thing we're interested in doing is characterizing that performance. But the other thing is you can provide some hints to the systems. You can say, I'm going to be accessing these pages on a particular device. And then it can do a bulk migration, which is faster. And so on these new systems, these are the two methods in green and red here, this coherence and prefetch. So coherence is that the GPU accesses a page that's on the CPU and it gets it on demand. Prefetch is when we hint to the CUDA system that we need to move in bulk these pages over to another device because it's going to be accessed there soon. And so you can see that if we use unified memory, we get the nice programmability benefits, but it comes at some performance cost. And so this is the CPU to GPU direction, and this is the GPU to CPU direction. So one thing to note is that the performance is kind of asymmetric. But the other thing to note is that if we do prefetch, we can capture a substantial amount of the sort of best performing transfer method. But if we're going to stick with coherence without really giving the driver many hints, then our performance degrades pretty badly. And particularly in this GPU to CPU direction, the CPU needs to use more than one thread to really even get a reasonable mad bandwidth. We're down here in the current Blue Waters bandwidth regime, so you can really give up a lot of performance. On systems, this is the system that's closer to Blue Waters. We see less of a performance hit from the unified memory system just because the peak performance is so much lower. So it's kind of nice. On these new systems, we get lots of performance, but it sort of opens us up to being able to shoot ourselves in the foot by making a bad choice on our implementation. And so the benchmarks that generate these plots are all available. And what we're looking at here is we have the standard deviation over a variety of runs at these little ticks. So you can see this is pretty repeatable data. And so another thing is that when there's more devices and more GPUs, the choice of where the data is and where it needs to be moved to can have a big impact on how fast the data gets there. So local refers to some pair of devices that are directly connected, and remote means more than one hop on that cartoon that I drew before. And so you can see that when we're doing unified memory prefetching, there's like a 2x performance difference. When we're doing bandwidth, or when we're doing coherence accesses at these intermediate transfer sizes, there's a pretty big difference. And even the sort of basic allocation, where I do allocation and memcopy explicitly, there's a big performance difference. And so we're looking to understand if we can help the CUDA runtime systems for particular applications, either look at the application, understand how much performance are we potentially giving up by doing it the wrong way, how much we could get back by doing it the right way, and maybe even have a runtime system that can help people make these right decisions when they're writing their code. And so the final thing that I want to touch on is if you're thinking about looking at neural networks for your own science domain problems, we've collected a wide variety of data on what I like to think of as these model machine framework triples. So when I'm writing a neural network, I have a particular neural network architecture in mind, runs in a particular framework, MXNet or TensorFlow, for example, runs on a particular machine with different performance characteristics. And so we have a wide variety of comparisons for neural networks that have been in the literature looking at the performance of these. And we also have quite a few neural network primitive benchmarks. So a convolution layer in MXNet particular sizes that we pulled from existing networks. And so if you're interested in looking at networks, or you have some network that you'd like a detailed performance analysis of, we would be extremely happy to work with you to gather that information and make it available to you. And so I've had a lot of help with a variety of these different tasks. Professor Hu, this is the team of Professor Hu's students and research scientists that worked on optimizing the GPU code, and we've had some collaboration with NVIDIA and IBM looking at some of these next generation systems and the performance of them. So I just want to acknowledge that. And thank you very much.